Thank you. So hello everyone. So my name is Nachshon Cohen, and today I'm going to talk about a programming language abstraction for non-volatile memory. And this is joint work with David Exton and Jim Laus. So the main contribution of this talk is C++ extension for supporting recovery for non-volatile memory that is very simple and easy to use. So let me start with some background. So what is all this non-volatile memory? So non-volatile memory is a new type of memory, basically offer DRAM-like performance. So it allows bi-granularity access, but then it also supports disk-like durability. So anything that's written into this memory is kept, even after shutting down the machine, whether it was planned or even unexpected. And already now we have NVDMs that use supercapacitors together with flash to support this non-volatile memory. But there's really excitement about this non-volatile memory because of some new memory technologies like 3D Crosspoint by Intel, STT-RAM, phase change memory, and some more. So how does the application running of non-volatile memory looks like? So the application is running, and then at some point, application running, then write some information to this non-volatile memory. Then at some point, the application terminates, again, due to some power failure, shutting down the machine. And then before rerunning the application again, we need to run some recovery to bring the non-volatile memory state to something that application can run again. And in fact, there's a lot of work on how to recovery in terms of consistency. So writing atomic blocks or fault-tolerant libraries to ensure that even if the application crashes in the middle of some operation, we're still able to resume the non-volatile memory to a consistent state. But today I want to talk about a different kind of recovery, and this is recovering the execution environment. And now, what is this execution environment, and what does it mean to have some information that is execution specific? So let me start with some example. So let's say I have an object A that resides on the non-volatile memory, and this object A has a pointer to an internet socket. Now, if we have a power failure, then after we execute the application, this socket pointer no longer exists. The socket itself no longer exists. We don't know what happened with the other machine. But the problem is that our object A actually resides on the non-volatile memory, so it is retained. And the problem is that now this object A has a pointer that points to nowhere. And so this object A is basically corrupted, or in general, the state of our non-volatile memory is corrupted. Now, this does not only affect a socket pointer. Same happen with locks. So locks is something, again, that relates to the specific execution. If a thread take a lock, we really don't want this lock to remain locked after the application shut down. Process facilities, fine handler, even there are several libraries written for non-volatile memory that purposefully keep some of the fields as transient to avoid some runtime cost. And the problem is, again, that after shutting down the machine and restarting, the object is not well formed for the current execution. But in fact, the problem goes even deeper. So even pointers are execution specific. Let me explain how non-volatile memory works. So initially, the system allocates a file on the non-volatile memory and then map it to the application virtual address space. Then after restarting the application, the system again locates this existing file and again map it to the application virtual address space. And this mapping is done typically using the mmap system call in Linux. And this mmap system call has as a first argument address where this virtual memory should be mapped. But the problem is that the kernel doesn't necessarily have to follow this address, and in fact can map the same address to a different location. And now suppose we have this object A that points to another object B that is right now has an address of 1,200. But now, if our kernel decided to map exactly the same memory to a different virtual location, our object A still has a pointer to 1,200, but there's no object B there. So at this point, you might ask, well, but probably our operating system will just give us always the same virtual memory, so we don't really have to care about this. Well, probably, but probably not. So recall that we're dealing with durable data. So we might have the operating system get updated. We might have a different memory, non-volatile memory become larger. We might execute the same application under a debugger or profiler. We might install a library that just decided to load at address 1,000. And in this case, the operating system cannot give us the same mapping address. And what we really don't want to have is after installing some library, someone telling us, sorry, but you cannot have the durable data because we cannot map to this address. In addition to pointers, we have the problem of code pointer. So if you're coding in C, probably your object has some function pointers. If you're coding in C++, probably the compiler inserted some virtual table pointer to your code. And actually, modern operating system has a feature called address space layout randomization, saying that every time you execute the program, the code is going to be loaded in a different location. And again, the point is, after you just shut down and restart the application, the object is not well formed anymore. So what was the existing solution to this problem? So there is some nice paper from ASP+11 saying, well, let us just forbid any pointer from non-volatile memory to DRAM, because what is the meaning of such a pointer, right? After restarting, this pointer is no longer valid. But then real application do this all the time, right? There are a lot of objects that has pointer to locks. We really don't want to just decouple anything. There are some ad hoc solutions, such as generational locks, self-relative pointers. So instead of storing the actual pointer, store some offset from the beginning of the non-volatile memory, which requires a lot of code changes. There are also a lot of comments. So here is a code snippet from a popular non-volatile memory system. And the author wrote there, put a lock and a pointer into an object that should reside on non-volatile memory. And they say, like, well, notice that these two fields should be transient. So please, please, please do reset all these variables every time you restart. And of course, you have to write a lot of initialization code to actually maintain this property. And of course, good luck with ensuring that this variant always followed. So how to make recovery more easily? So NVM Reconstruction is a system that provides object-level recovery. And the main idea is that it's not sufficient just to ensure that your transaction either completed or aborted, but you really need to ensure that every object is actually well-formed and matches the current execution environment. And we want to do this in a manner that is transparent to the application as much as possible. So this is how a programmer would use NVM reconstruction. So first, notice that the application can just use standard pointers and no need to store offsets. In addition, the programmer can use a transient modifier, saying that our lock is transient, which means that when we restart the application, the system will ensure that this lock is zeroed out before the application continues. If there is need to do something smarter, it's also possible to use a reconstructor that basically execute some arbitrary code to, again, make the object well-behaving with respect to the current execution environment. And finally, it also defines pnew and pdelete for allocating and deallocating memory on the non-volatile memory. So how all this magic work? So from the system perspective, what we really need to do is, during recovery, we want to basically iterate over every live object in the heap, and then zero transient field, rebase NVM pointer, fix the code pointer, like function pointer, virtual table pointer, and then execute the user-provided reconstructor. For all this, we really need to have some runtime type information. So toward this, we wrote a Clang LLVM plugin that generates this type information. In addition, we have a runtime system that generates runtime information, such as a mapping address, where the NVM was mapped, and store all this information in the non-volatile memory. And it also has an allocator that attaches a header for each object saying what is the type of this object. Now, during recovery, so the system basically gathers all this type information from the previous execution and then compute the delta from the current execution. And this is done on a per-page basis. So why does it need to do this on a per-page? So in fact, because we might have multiple crashes in the application, so it might be that every object, a different object in our system, will allocate at different stages of the application. So for example, we might have a non-volatile memory that is mapped to address 2000. And then we might have an object B that was allocated when the mapping address was 1500. And for this case, every pointer needs to be fixed by 500. And in addition, we might have another object A that was allocated when the mapping address was 1000. And for the A object, every pointer needs to be fixed by 1000. And the same happens also for code pointer. On each execution, we might have a different pointers, a different location where the function pointers were loaded. In addition to all this, it's really important to avoid the case where we have very long reconstruction time. So we really don't want to execute the entire recovery just before the application starts, because then, especially if the NVM becomes larger, we'll have to wait a lot until the application starts. So we use a standard system technique. So instead of just mapping the non-volatile memory, we map it without memory protection. So every time we read or write to the non-volatile memory, going to capture a trap and then execute all the recovery code on the object that resides on this page. Another very important capability of our system is compaction. So typically, when we deal with transient memory, we only have one version of our program. But when we're moving to a durable object, this is no longer correct. So we have our application version 1. And then at some point, we decide that we really need our B object to contain an additional field. And if we're going to do this just naively, then these B objects are already allocated in the non-volatile memory. There is no additional space to allocate this additional field. If you're going to do this just naively, then this is going to cause a overlapping of the memory and override of important information. So because we already have type information for all our objects, an additional problem we have is fragmentation, right? Because again, we're dealing with durable information. We might have this heap getting a lot of allocation, deallocation stuff, and eventually we might have a lot of small holes in the heap that are not usable for allocating new data. And again, because we already have all the type information, what the NVM reconstruction do on an offline stage is just to recompact anything and handle all this updating of the object version. So we basically just increase the size of every object, every B object, and then pack them to the beginning of the heap, reducing fragmentation and enabling such enlarging of objects. We incorporated NVM reconstruction into two systems. One system is Atlas, which is a popular non-volatile memory system. Atlas itself does not support transient field. It only allows you to map non-volatile memory to some fixed address. If not, the non-volatile memory become inaccessible. And all this is fixed using our NVM reconstruction. The overall cost using normal runtime is quite negligible. It's less than 1%. The only overhead is the initialization time, when we basically have some fault storm, when we need to fix all pages that are accessed. And we measure that somewhere around up to 200 millisecond per gigabyte heap. Of course, it really depends on what is the exact access pattern of the application. In addition to Atlas, we also incorporated the NVM reconstruction into the Echo key value store. So Echo is the key value store designed specifically for non-volatile memory. It's not really a small piece of code. It's over 22,000 line of code. However, the open source provide no recovery function. And in fact, if you just try to crash Echo and rerun it again, it's going to crash because it uses some function pointers that are not handled correctly after restarting the application. And apparently, this is quite a hard thing to do. But using NVM reconstruction, we're able to add full recovery by adding just 214 line of code, which show how easy it is to use this and to provide full recovery easily. So just to conclude, the execution environment may change after a restart. And it's really important not only to consider the consistency of the non-volatile memory, but also whether our non-volatile memory actually fit the execution environment we are in. And NVM reconstruction is a system-level approach for providing this object-level recovery. It provides transient fields, virtual address pointer, custom reconstruction to make all this easy. Overhead is quite low, and it makes writing recovery much easy. So thank you all for listening, and I'll be happy to take questions.
Questions? Over there. Hi, great talk. I'm going to ask a question about a slightly different domain that I think might be applicable. Some of my work, I'm working off of RDMA devices. And one of the promises of RDMA is the idea that you can get memory out of another dynamic participant without going through their CPU. It seems like the same sort of problems of changing execution domain are present there. Do you suspect that your technique would just kind of work unmodified, or what do you think we would have to do to adapt it to that domain?
Yeah, actually, it's a very interesting thing, and I actually started looking at this, even though I didn't complete this. Certainly, actually, one of the tests we conducted is saying like the entire environment may change, and we actually created the NVM heap on a Linux machine, and then transfer it and run the recovery on a Mac machine, and yeah, this recovery worked. And I think it's really exciting, but I didn't have a chance to really develop something that I think it's definitely applicable and important.
Thanks.
Any other questions?